So in the previous lecture, we introduced the maximal tensor product of C-star algebras. So let's recall the construction. So suppose we have two C-star algebras, A and B. And then we define the maximal norm, maximal C-star norm on their algebraic tensor product as follows. It is defined to be the supremum of the norms of pi of u, where pi runs over the set or the class of all star representations of the algebraic tensor product. So what is not clear from this definition is that, that this number is finite. In fact, it is finite, and this was proved at the end of the previous lecture. More exactly, we proved the following theorem. First of all, this number is indeed finite. This is finite for each u in the algebraic tensor product. And so this number defines a C-star norm on the algebraic tensor product. It is indeed a norm and not a semi-norm, because it is obviously dominates the minimal or the spatial C-star norm, and the spatial C-star norm is indeed a norm. Property 2, if we have a C-star algebra C, so for each C-star algebra C, and for each star homomorphism phi from the algebraic tensor product of A and B to C, we have the following inequality. The norm of phi of u is less than or equal to the maximal C-star norm of u. So in other words, each star homomorphism from the algebraic tensor product to any C-star algebra is bounded and is moreover contractive with respect to the maximal C-star norm. This property implies the next one, part 3, namely the maximal C-star norm is indeed the largest C-star norm on the algebraic tensor product. And finally, property 4 tells us that the maximal C-star norm, like the spatial C-star norm, is a cross norm, in the sense that if we take an arbitrary elementary tensor, then the norm of this element is equal to the product of the norms of A and B. Okay, and at the very end of the previous lecture, we introduced the maximal C-star tensor product. So we gave the following definition. The maximal tensor product of A and B is defined to be the completion of the algebraic tensor product with respect to the maximal C-star norm. So it is a sister algebra. Okay, let's now look at some corollaries of this result, of this theorem. Corollary 1. For each sister algebra C, each star homomorphism phi from the algebraic tensor product of A and B to C uniquely extends to the maximal C-star tensor product. Uniquely extends to a star homomorphism from the maximal tensor product to C. This is immediate from part 2 for our theorem, because part 2 implies that phi is automatically bounded with respect to the maximal C-star norm. So we can simply extend it by continuity to the completion, that is to the maximal tensor product of A and B. Okay, the next result is kind of quasi-universal property of the maximal tensor product. So suppose that we have a C-star algebra C. Suppose that C is a C-star algebra. And suppose that we have a pair of star homomorphisms. So phi is a star homomorphism from A to C, and psi is a star homomorphism from B to C. Star homomorphisms. Then, and suppose that phi and psi commute, phi and psi commute in the sense that their images commute. So this is a short notation for the property that phi of A and psi of B commute for each A and B. I claim that in this case, there exists a unique star homomorphism, that's denoted by pi, from the maximal tensor product of A and B to C, such that pi takes each elementary tensor, A tensor B, to the product of phi of A and psi of B. So to prove this corollary, it's enough to apply corollary 1. Just apply corollary 1 to the homomorphism, which was denoted at the previous lecture like this, phi cross psi. This is the homomorphism from the algebraic tensor product of A and B to C, and it is uniquely determined by the following formula. So since the images of phi and psi commute, it follows that this map is indeed a star homomorphism. So we just apply corollary 1 to this homomorphism, and we get the required extension to the maximal tensor product. Well, why do I call this property a quasi-universal property? Unfortunately, it turns out that not every pi comes from such a pair. This is a useful exercise. Not every star homomorphism pi from the maximal tensor product of A and B to C comes from such a pair. So in general, we have no bijection between such pairs of commuting star homomorphism from A to C and B to C, and the set of all star homomorphism from the maximal tensor product of A and B to C. But in the special case where C is the algebra of bounded operators on a Hilbert space, everything is okay. And this is our corollary 3. There is a one-to-one correspondence between the set of all star representations, of non-degenerate star representations, of the maximal tensor product of A and B on an arbitrary Hilbert space H, and the set of all pairs pi1, pi2, where pi1 and pi2 are non-degenerate star representations of A and B respectively on the same Hilbert space H, such that pi1 and pi2 commute. So we have a one-to-one correspondence between these sets. And this follows from corollary 2, combined with a theorem from the previous lecture, which was stated but which was not proved, and which states that if we start with a non-degenerate representation of the algebraic tensor product on a Hilbert space, then every such representation gives provides two representations, pi1 and pi2, of the algebras A and B respectively. So this result wasn't proved, but it will be included together with some hints into our next exercise sheet. Roughly, we discussed why it is true in the unital case. And in the non-unital case, we have to replace the identity by a suitable approximate identity. Okay, now before we formulate the next corollary, we will need the following lemma. Suppose that A and B are C-star algebras. And suppose that phi is a star homomorphism from A to B. I claim that phi, the image of phi, is always closed. Phi A is closed in B, and moreover, the norm of phi equals 1, except for the trivial case where phi is 0. By the way, let's recall that we already know that each star homomorphism between C-star algebras is automatically bounded, and the norm of this homomorphism is less than or equal to 1. And now I claim that the image of such homomorphism is always closed. The proof is just a combination of some facts that we already know about. So let's draw a picture. This is our homomorphism phi. So we can consider the quotient of A modulo the kernel of phi. So the kernel of phi is a closed two-sided star ideal. So the quotient becomes a C-star algebra. And we can factorize phi through the quotient. So we get a star homomorphism phi hat, which makes this diagram commute, and which is injective. Phi hat is injective. But we already know that an injective homomorphism, an injective star homomorphism between C-star algebras is isometric. So phi hat is isometric, and the image of an isometric operator between Banach spaces is closed. So the image of phi hat is closed. But this is nothing but the image of phi. Okay, and to show that the norm of phi is 1, so let's denote by Q the quotient map from A onto the quotient. So since phi hat is isometric, it follows that the norm of phi equals the norm of Q. And of course, the norm of Q is 1 unless phi is 0. Okay, so this completes the proof of our lemma. So now we come back to tensor products, and we have one more corollary 4. So I claim that if you take the identity map of the algebraic tensor product, then this map extends to a surjective star homomorphism. From the maximal tensor product of A and B onto the minimal or the spatial tensor product of A and B. Well, why is it so? Well, first of all, we just apply corollary 1. Let's look at corollary 1 again. So we take the inclusion of the algebraic tensor product into the minimal tensor product, and we extend this inclusion to the maximal tensor product by corollary 1. So we get this star homomorphism from the maximal tensor product to the minimal tensor product. Clearly, its image is dense because it contains the algebraic tensor product, which is dense in the minimal tensor product. But on the other hand, we already know that the image is always closed, and so this map is surjective. Okay, so now we come to the following natural question. Is it true that this homomorphism is actually an isomorphism? In general, the answer is no, and this leads to the following definition. If we have a sister algebra A, and we say that A is nuclear, if for every sister algebra B, the maximal norm and the minimal norm on their tensor product are the same. We have the following equality. On the algebraic tensor product. And this is obviously equivalent to the statement that this homomorphism from the previous corollary, the homomorphism from the maximal tensor product onto the minimal tensor product, is an isomorphism. This is clearly equivalent because if it is an isomorphism, then it is automatically isometric, and so the maximal and the minimal C-star norms are the same. In Russian, nuclear is ядерная. Okay, so how about examples of nuclear algebras? In fact, we already know about one of the examples. We know that the matrix algebra, the algebra of square n by n matrices, is nuclear. because we proved some time ago that there is a unique C-star norm. For each C-star algebra B, there is a unique C-star norm on the tensor product. On the tensor product of M, N, and B. So the matrix algebra is nuclear. Another example, which generalizes the matrix algebra, an example and exercise at the same time. I claim that each finite dimensional C-star algebra, each finite dimensional C-star algebra is isomorphic to a finite direct sum of matrix algebras. And by using this, it's easy to deduce that a finite dimensional C-star algebra is nuclear. Well, now how about infinite dimension examples? We have the following general theorem, which says roughly that if a C-star algebra can be approximated by nuclear C-star subalgebras, then it is nuclear. More exactly, the result is the following. Suppose that A is a C-star algebra, and suppose that B, script B, is a directed family, of C-star subalgebras of A. Directed means the following. If you take arbitrary algebras B1 and B2 from this family, we can always find another subalgebra B3 in the same family, such that this subalgebra contains B1 and B2. Okay, and suppose that this family is big. Suppose that the union of this family is dense in A. And suppose that each algebra in this family is nuclear. I claim that in this case, A is also nuclear. Well, to prove the result, we just check the definition. So we take an arbitrary C-star algebra C. C is an arbitrary C-star algebra. And let A0 denote the union of the family B. Well, since this family is directed, it follows that A0 is a star subalgebra, and it is dense. So A0 is a dense star subalgebra of A. If I now take the algebraic tensor product of A0 and C, then by the simple properties of the algebraic tensor product, this algebra becomes a union, a directed union of the subalgebras B tensor C, where B runs over our family script B. And now, since each of the algebras B in our family is nuclear, and because of this equality, it follows that the maximal and the minimal sister norms are equal on this algebra. On A0 tensor C. And now, to complete the proof, we observe that this algebraic tensor product, A0 tensor C, is dense in the algebraic tensor product of A and C with respect to the maximal tensor norm. In fact, this is a little exercise for you to prove the density. Basically, this follows from the fact that A0 is dense on A, and from the fact that the maximal C-star norm is a cross norm. So the norm of each elementary tensor is the product of the norms. Okay, so it is dense. Let's also recall that the minimal C-star norm is less than or equal to the maximal C-star norm. And so it is continuous with respect to the maximal C-star norm. So we have two norms, min and max, on the same algebra A tensor C, and min is less than or equal to max, and they are the same on the dense subalgebra A0 tensor C. So by continuity, they are the same everywhere. And this means, precisely by definition, this means that A is nuclear. Okay, let's now apply this result to the following concrete situation. We have the following corollary. The algebra of compact operators on an arbitrary Hilbert space H is nuclear. To prove this corollary, we do the following. Suppose that L is a finite dimensional vector subspace of H. And let PL denote the orthogonal projection onto L. Now, for each such finite dimensional subspace, we introduce a subalgebra in K of H, we denote it by AL. And this subalgebra consists of all operators of the following form: PL, T, PL, where T runs over K of H. It's a simple exercise to show that AL is a star subalgebra in K of H. Star subalgebra of K of H. And this subalgebra is isomorphic to the matrix algebra, the algebra of all n by n matrices, where n is the dimension of L. This is a simple exercise. Okay, and now let's consider all algebras of this form, and let's denote their family by B. So here L runs over the family of all finite dimensional subspaces of H. Again, it's a useful exercise for you to show that B satisfies the conditions of our previous theorem. Well, it's clear that they are nuclear because each of them is isomorphic to a matrix algebra, and so the exercise is to show that their union is dense. Well, basically, this is more or less equivalent to the fact that, which was also mentioned some time ago at our lectures, the fact that such orthogonal projections PL, where L runs over the family of finite dimensional subspaces, form an approximate identity in our algebra. So this fact is more or less equivalent to the fact that the union of the subalgebras AL is dense in KOH. And so by the previous theorem, KOH is nuclear. Okay, how about other standard examples of C-star algebras? Here I can only formulate some facts without proofs. First of all, it's a deep theorem by Takesaki that each commutative C-star algebra is nuclear. Each commutative C-star algebra is nuclear. This is not trivial, and the proof is not short. So I state this result without proof. And as for counterexamples, the first counterexample is also due to Takesaki, and it is the reduced C-star algebra of the free group of two generators. This algebra is not nuclear. More exactly, Takesaki proved that, let's look at one of our previous results, namely corollary 2. So Takesaki proved if we take here A and B to be the reduced C-star algebra of the free group of two generators, then we cannot replace here the maximal tensor product by the spatial tensor product. So he proved that if you take the minimal tensor product here, then the respective homomorphism is unbounded on the algebraic tensor product. And as a result, the maximal tensor product are not the same. And another example, due to Pirkovskii, is that BOH, the algebra of bounded operators on any infinite dimensional Hilbert space, is not nuclear. This is 1981. Okay, well, that's all I wanted to tell you about the maximal tensor product and nuclear C-star algebras. Maybe I'll give one final remark, which explains why nuclear C-star algebras are so called. Briefly, the reason is that they are called nuclear by simple analogy with nuclear locally convex spaces introduced by Grothendieck. In fact, if we look at Banach spaces, then there are at least two natural tensor products of Banach spaces. The so-called projective tensor product, denoted like this, the projective tensor product, and the injective tensor product, denoted like this. So each of them is defined as the completion of the algebraic tensor product with respect to a suitable cross norm. This is the projective tensor product. And the injective tensor product. And we take the completions here. So the tilde denotes the completion. The projective tensor norm has the property of being the biggest cross norm on the algebraic tensor product. And the ejective tensor norm is the smallest reasonable. At this point, I don't say what reasonable means, but it's the smallest reasonable cross norm on the algebraic tensor product. And in particular, we have the following inequality. And this inequality gives us the following canonical map from the projective tensor product to the injective tensor product. In general, this map is not surjective and is not injective, but it extends the identity map on the algebraic tensor product. So this is the situation with Banach spaces. In fact, similar constructions can be made for arbitrary locally convex spaces, X and Y. And by definition, if X is a locally convex space, then we say that X is nuclear if for each locally convex space Y, the above map is a topological isomorphism. Nuclear spaces were introduced by Groth and Deacon in the 1950s, and they are called nuclear because they are closely related to nuclear operators, and in fact then can be defined in terms of nuclear operators. Nuclear operators are very classical objects of functional analysis. The class of nuclear spaces is rather big. It contains many important spaces of functions and distributions. In particular, all spaces of smooth functions on smooth real manifolds are nuclear. Spaces of holomorphic functions on complex analytic manifolds are nuclear. The Schwarz space is nuclear. The space of compactly supported distributions is nuclear. And the space of tempered distributions is nuclear, and so on. On the other hand, it's important to remember that a normed space is nuclear if and only if it is finite dimensional. So in particular, if we look at a sister algebra, then a sister algebra can be nuclear as a locally convex space only if it is finite dimensional. So once again, I'd like to stress that nuclear sister algebras are almost never nuclear as locally convex spaces. And the definition is, the terminology is given just by an analogy. So if we look at this definition of a nuclear locally convex space, then it looks very similar to our definition of a nuclear sister algebra. We just replace the projective tensor product by the maximal sister tensor product and the injective tensor product by the minimal sister tensor product. Another natural question is the following. Can we extend the maximal or the minimal sister tensor products to the category of Banach spaces? Well, in general, there are two natural candidates for such an extension, namely the projective and the injective tensor products. So in the general case, we have the following chain of inequalities. If we take two sister algebras A and B, then the injective tensor norm is less than or equal to the minimal C star tensor norm. This is less than or equal to the maximal C star tensor norm. And this is less than or equal to the projective tensor norm. In general case, the inequalities are strict. And in particular, the first two norms, the injective and the minimal, it's known that they are the same provided that either of the algebras is commutative. But if both A and B are non-commutative, then the injective tensor norm is not a C-star norm in the general case. And the projective tensor norm is almost never a C-star norm, even if A and B are finite dimensional. In fact, it turns out that the minimal C-star tensor norm, well, first of all, none of them can be extended to the category of Banach spaces, but it turns out that the minimal C-star tensor norm can be extended to the category of so-called operator spaces. But this is a different story, so I don't plan to tell you anything about operator spaces in this course. Okay, so that's all I wanted to tell you about tensor products of C-star algebras. Now, before we begin discussing compact quantum groups, let's discuss another general C-star algebraic construction, which will be very useful for us because it is this construction will enable us to construct many concrete examples of compact quantum groups. And the construction is called the C-star envelope. So suppose that we have a star algebra A. It's just a star algebra. So the C-star envelope way is a kind of universal completion way. Universal C-star completion. The formal definition looks as follows. A C-star envelope of A is a pair consisting of a C-star algebra C-star of A so C-star of A is a C-star algebra and theta is a star homomorphism from A to C-star of A such that the following universal property holds. So let me draw a picture. This is A, this is C-star of A, this is theta. So the property is that for each C-star algebra B, so this is our B, and for each star homomorphism phi from A to B, and this is phi on the picture, there is a unique star homomorphism psi from C star of A to B this is psi, such that the diagram commutes. So this is a very natural universal property, which looks similar to, say, the universal property of the completion of a metric space, or to the universal property of a universal enveloping algebra for Lie algebra, and to many other universal properties which exist in mathematics. Okay, what can we say immediately by looking at the definition is that a C-star envelope is unique in the following obvious sense. So let's observe that if we have two C-star envelopes of the same star algebra A, say C-star 1 of A and C-star 2 of A, with respective homomorphisms theta 1 and theta 2, Then there exists a unique star isomorphism psi. There is a unique star isomorphism psi such that the diagram is commutative. This is immediate from the definition. Okay, now how about the existence of the C-star envelope? To study the question of existence, let's introduce some terminology and some notation. By definition, a C-star seminorm on A is a function P. Well, first of all, it's a seminorm. It's a seminorm. Say P on A, such that, first of all, it is submultiplicative. P of AB is less than or equal to P of A, P of B. Second, the involution is isometric with respect to P. And finally, P satisfies the C-star identity. P of A star A equals P of A squared for all A and B in our algebra. In other words, a C-star seminorm is something like a C-star norm, which is allowed to vanish on non-zero elements. Okay, now let's introduce some notation. Suppose that P is a C-star seminorm. On A. And let IP denote the set where P vanishes. It's immediate from the above definition that IP is a two-sided star ideal. A two-sided star ideal of A. So we can consider the quotient of A modulo this ideal, and let's denote it by AP0. This quotient is equipped with a C-star norm, which is well defined by the following formula. So the norm of each element in the quotient is the seminorm of any representative of this element. It's a simple exercise to show that this is well defined, and this is a C-star norm. This is a C-star norm on AP0. So AP0 becomes a pre-C-star algebra. And so we can take the completion of this pre-C-star algebra, and this completion will be denoted by AP. And this is now a C-star algebra. AP is a C-star algebra. And we have a canonical map, pi p, from A to AP, which is just the composition of the quotient map with the inclusion of AP0 into its completion. Clearly, it's a star homomorphism. Okay, and now let's define something like a C-star seminorm on A by the following formula. So for each element A in our algebra, we introduce the following number, which will be denoted like this. And this is the supremum of P of A, where P runs over the family of all C-star seminorms on A. So this is some non-negative number, which sometimes can be equal to infinity. And I don't claim that it is always finite. We now have the following proposition. First of all, I claim that the same number can be defined as follows. This is the supremum of the norms of pi of A, where pi runs over the class of all star representations of A. Looks similar to our definition of the maximal C-star norm on the tensor product, isn't it? Well, and we will see later that indeed the C-star envelope, the notion of a C-star envelope extends the maximal C-star tensor product. The second part of this proposition, I claim that the C-star envelope of A exists if and only if this number is finite. This is finite for each A in our algebra. And part 3, if it is finite, so suppose that it is finite, for each A in our algebra, I claim that in this case, the C-star envelope can be described explicitly as follows. First of all, this function, which is now finite, that's denoted by P. This is a C-star seminorm, and moreover, this is the largest C-star seminorm on A. This is the largest C-star seminorm on A. And if we look at the respective C-star algebra AP, together with the homomorphism pi P, and this pair is a C-star envelope of A. Okay, so let's now prove this result. Well, first of all, if we look at part 1, it's more or less clear that the right-hand side here is less than or equal to the left-hand side. So the left-hand side is defined in terms of C-star seminorms. Well, indeed, this is more or less clear. This inequality is clear because for each representation pi, the function which takes A to the norm of pi of A is a C-star seminorm. This is a C-star seminorm. And so this supremum is less than or equal to this supremum. And to prove the opposite inequality, we must show that each C-star seminorm is less than or equal to this supremum. So we take a C-star seminorm. Suppose that P is a C-star seminorm on A. We take the respective C-star algebra AP and find a faithful star representation, tau of AP. Then for each element A in our algebra, we have the following equalities. Pi of A equals the norm of its image in AP, simply by the definition of the respective norm on AP. And since tau is faithful, it is isometric, so we can write this in the following way. But this composition of pi, p, and tau is a star representation of A. And so this shows that P is dominated by, is less than or equal to this supplement. Okay, so let's now look at property 2. First of all, we observe that, first of all, we prove the left-to-right implication. So suppose that C star of A exists. Again, we take an arbitrary C star semi-norm on A, and we look at the following picture. So this is A. This is the canonical homomorphism pi p to the C star algebra AP. And here we have the C star envelope. And by the definition of the C star envelope, we have a star homomorphism here, as denoted by psi p. And now, so P of A for each element in our algebra, P of A is the norm of pi P of A. By the commutativity of the diagram, this is nothing but psi p theta of A. But psi p is a star homomorphism between C star algebras, so its norm is less than or equal to 1. So this is less than or equal to the norm of theta of A. And this doesn't depend on P. So when we take the supremum over all C star semi-norms, we conclude that this number is less than or equal to theta of A. And so it is finite. Okay. And finally, we prove the right to left implication. So we suppose that this is finite. This is the right to left implication in part 2. And at the same time, we prove part 3. So we suppose that this is finite. We denote it by P. And we will show that AP together with pi p is a C star envelope of it. So let's look at the following picture. Maybe I'll draw it here. So this is A. This is B. And this is phi. So suppose that B is a C star algebra. And phi is a star homomorphism from A to B. So we want to extend phi to AP. So let me put AP0 here. So we have a quotient map here. And AP0 is the dense subalgebra of AP. And the composition of these two arrows is pi p. So we first of all we construct a C star semi-norm on A by the following formula. Q of A is the norm of phi of A. And this is a C star semi-norm on A. Well, by assumption, our semi-norm P, where is it? Here it is. So our semi-norm P is finite, and of course, by definition, it is the largest C star semi-norm. So it is, since it is the largest C star semi-norm, we conclude that Q is less than or equal to P. Q is less than or equal to P. In particular, this inequality implies that phi vanishes at IP. IP is the ideal where P vanishes. So if P vanishes on some element, then Q vanishes, or equivalently phi vanishes on the same element. And so we can factorize phi through the quotient. So there is a unique star homomorphism phi 0, making this diagram commute. Okay, let's now look again at this inequality, and let's observe that this inequality implies that psi 0 is bounded. Well, indeed, psi 0, when we apply psi 0 to any element in the quotient a plus ip, this will be phi of a, and this is q of a, and this is less than or equal to p of a. So this inequality implies that psi 0 is bounded. Psi 0 is bounded, and so it uniquely extends to the completion. Psi 0 uniquely extends to a star homomorphism psi from AP to B. And this completes the proof. So we see that AP is indeed a C-star envelope of our algebra. Okay. It turns out that there are some simple examples of star algebras for which the above condition is not satisfied, and so the C-star envelope doesn't exist. But before we discuss such examples, so before we discuss good examples and bad examples, so the good examples are the examples where the C-star envelope exists and is big enough, and the bad examples is the examples where the C-star envelope doesn't exist. So before we discuss such examples, let's look at some simple condition which guarantees the existence of C-star envelope. So we have the following proposition. Suppose that A is a star algebra, and we suppose that A is generated as a star algebra by a certain set S. And suppose that for each element A in the set, there is a positive constant C, such that for each C-star seminorm P on A, we have the following inequality. P of A is less than or equal to C. I claim that in this case, the C-star envelope of A exists. The proof is very easy. We simply observe that each element in A has the following form. It can be written as a finite sum of products of elements in S or in S star. This is a finite sum where each element Aij sits either in S or in S star. simply because such a representation is always possible, simply because A is generated by S as a star algebra. So by assumption, if we take now a C-star seminorm P, then P of each Aij is less than or equal to C. And now the triangle inequality implies that there is a positive constant D, which depends only on A, such that P of A is less than or equal to D, where D doesn't depend on P. And this always implies that if we take the supremum over P, we conclude that our seminorm A star is finite, which means that the C-star envelope exists. Here is an important special case of this situation. So we have the following proposition. Suppose that A is a unital star algebra, and suppose that little u is a unitary matrix, a unitary square matrix over A. I claim that for each C-star seminorm, on A, the matrix entries of U, the norms of the matrix entries of U are less than or equal to 1. To prove this proposition, we observe that, first of all, we may assume from the very beginning that A is a C-star algebra. We may assume that A is a C-star algebra, because if it is not, then we replace A by the respective C-star algebra AP. Consider the C-star algebra AP, where P is our seminorm. So since P of A is the same as the norm of the image of this element in AP, we reduce everything to the algebra AP. Now AP is a C-star algebra, so by the Gelfand-Nymark theorem, it is asymmetrically embedded into some B of H, or some Hilbert space H. And so by replacing AP by B of H, we may prove, we see that it suffices to prove our proposition for the algebra B of H. So we may assume that A is just B of H. Well, this is, well, since we have already assumed that A is C-star algebra, I remove B here. And so we reduce everything to the case where A is B of H. Okay, so U is a unitary matrix M in Mn of B of H. And Mn of B of H is nothing but the algebra of bounded operators on H to the power n. So what is now Uij? Well, Uij is the following composition: Pi U Ej, where Pi is the respective projection, is the projection of Hn onto H, on the ith copy of H, and Ej is the inclusion of H into Hn. it's clear from the notation what EJ is. So we just, well, let me maybe draw it explicitly. So this is how EJ how it acts. Okay, now if we now calculate the norm of UIJ, so since the norm of PI and EJ is less than or equal to 1, we see that this is less than or equal to the norm of U, but U is unitary, and the norm of a unitary operator is always 1 for each I and J. And so this completes the proof. Okay, if we now combine two previous propositions, then we come to the following corollary. Suppose that A is a unital star algebra generated by the matrix entries, generated by the entries of a family of unitary matrices. A family of unitary matrices over A. Then the C-star envelope of A exists. This is simply a combination of two previous results, because we know that if we take the entries of these matrices, then by the previous proposition, for each C-star seminorm, each C-star seminorm is bounded by 1 on these entries. And now applying this result, we see that the C-star envelope of A exists. This corollary is very useful because we will often meet such a situation when we discuss compact quantum groups. In fact, many concrete examples of compact quantum groups are defined to be the C-star envelopes of unital star algebras generated by entries of unitary matrices. Okay, in conclusion, let me introduce some useful standard terminology. Very often, and especially in the theory of quantum groups, we'll meet C-star algebras defined by generators and relations. Basically, this notion can be reduced to the notion of a C-star envelope as follows. So suppose that we have a set, suppose that I is a set, and let's denote by F the free algebra, the free associative algebra, generated by the letters xi and yi, where I runs over our set. This is the free algebra. So the standard basis of this algebra consists of words, arbitrary words in the letters xi and yi for all I. Let's first of all observe that there is an involution on F. F becomes a star algebra with respect to the involution, uniquely determined by the following condition, namely by the condition that xi star equals yi for each I. So we define the involution of the generators and then extend it to the whole algebra by using the axioms of the involution. And so the free algebra, this free algebra becomes a star algebra. Suppose now that we have a family, some family of elements in this algebra, Pj, family of elements of F. And let K denote the two-sided star ideal. Two-sided star ideal of F generated by this family. Of course, I mean generated as a star ideal. That is, this is the smallest two-sided star ideal of F, which contains all the elements Pj. We now define the universal unital C-star algebra. The universal unital C-star algebra generated by the letters xi with relations pj as follows. We denote it in the following way. And by definition, this is the C-star envelope of the quotient of F modulo K. If it exists, of course. Okay, so this is the definition, and it's immediate from the definition of the C-star envelope that this universal C-star algebra has the following universal property. For each C-star algebra A, and for each family of elements, family yi, of elements of A, such that each free polynomial Pj vanishes on yi and yi star, for each j, there is a unique star homomorphism, a unique unital star homomorphism, say alpha, from the universal C-star algebra to A, which takes each xi to yi. Well, this property is almost immediate from the definition, because first of all, we define our homomorphism on the free algebra, because it is free. So we can send the generators xi to our family, and xi star will go to y star, and we get a star homomorphism from F to A. This homomorphism vanishes on the ideal K because of this condition. So we get a star homomorphism from F modulo K to A. And then we use the definition of the C-star envelope and extend this homomorphism to the whole C-star algebra. And we get this universal property. And sometimes we will need to consider the universal commutative C-star algebra with the same property. So we introduce some more notation. We define the universal commutative C-star algebra generated by the elements xi with relations pj, as follows. This is the universal sister algebra generated by the same elements, xi, the same relations pj, and also the computation relations between the generators, xi, xk minus xk and xi, and the same for the adjoints. And it easily follows from the definition that this universal commutative sister algebra has a similar universal property, but now only in the category of commutative sister algebras. Okay, okay, so that's all for today. Unfortunately, we had no time today to discuss concrete examples of sister envelopes. So at the very beginning of the next lecture, we discuss such examples. In particular, we will discuss some examples where sister envelope exists and is big enough, and some other examples in which it is trivial or in which it doesn't exist. And after that, we introduce compact quantum groups and construct some examples of compact quantum groups. Okay, thank you.
Спасибо. До свидания.
Спасибо.